That is, we considered a system which can be brought into contact with either one of two reservoirs, one at a high temperature, T sub h, the other at a low temperature, tau sub L. The heat engine takes in heat from the high temperature reservoir, releases some heat to the low temperature reservoir, so there's some heat flow from high to low temperature. And the system outputs some useful work. The ideal heat engine works reversibly and undergoes a closed cycle. Since it's a closed cycle, the internal energy of the system returns to its initial value when the cycle is complete. The state of the system is the same as it was initially. Since it's reversible, the entropy of the universe stays the same. So the amount, I'll call it delta sigma n, by which the entropy of the system increases when heat flows from the high temperature reservoir into the system, equals delta sigma out, the amount by which the entropy of the system decreases when heat flows out of the system into the low temperature reservoir. And so we saw from those two conditions that it followed that the work done in a cycle, I'll call it W, because delta U is equal to 0, it's just the difference between the heat taken in and the heat expelled. And because of the reversibility condition, I can write that as the difference between the high and low temperatures divided by the high temperature times the heat taken in. Now, this coefficient is a measure of the efficiency of the heat engine, how efficiently it converts the heat that it takes in from the high temperature reservoir to useful work. This efficiency that's attained by the ideal reversible engine we call the Carnot efficiency. And we see that if the low temperature reservoir is not 0, then that ideal efficiency is strictly less than 1. There's always some waste heat. Some heat that has to be expelled to the low temperature reservoir, so the work done is strictly less than the amount of heat taken in at high temperature. So if you are a pessimist, you could summarize what we learned about heat engines in 3 laws. The first one is you can't win. That's the statement of conservation of energy. Which from the perspective of the pessimist is that we can't do any more work than the amount of heat that we take in. Either less than or equal to the amount of heat used by the engine. And if that's not depressing enough, the second law says you can't break even. But there is a caveat, except at absolute 0. In other words, if the low temperature reservoir has a positive temperature, as I just said, then the work done is strictly less than the amount of heat taken in. There's inevitably waste heat in a closed reversible cycle. Of course, there's always the hope that you can work at absolute zero and break even, and that's the purpose of the third law, is to dispel that moment of optimism. It says you can't get to absolute zero. We haven't talked much about the third law, partly because from our perspective it's kind of trivial. It says that entropy equals constant at zero temperature. Constant as a function of whatever other control parameters we can adjust for the system. The reason I say from our perspective it's trivial is we know that at zero temperature the system is in its exact ground state, and we can interpret the exponential of the entropy as the system's degeneracy. So e to the sigma at t tau equals 0 is ground state degeneracy. And that's just some non-zero constant, generically 1, potentially more than 1, if there's a system degeneracy imposed by, say, by some kind of symmetry. In the case where there's no ground state degeneracy at all, then we could say the constant is 0. So the pessimistic perspective on the third law is that, well, we might hope that if we can perfectly isolate the system from a reservoir, that we can then adiabatically change the system in such a way as to cool it to zero temperature. If we consider some parameters, just as an example, pressure and volume, there's an isentropic curve at t equals 0. So I'll call it the t equals 0 adiabat. Or maybe I won't, but maybe I'll make another attempt to do so. Where the entropy is constant. So in this PV plane, there are curves, isentropic curves of constant entropy. And as we, say, adjust the volume, the system will move along these curves. But the different adiabats, the different isentropic curves, each of which have distinct values of the entropy, never cross. So if I'm at some non-zero temperature, make an adiabatic change, I'll move along here, but I'll never reach the zero temperature surface here. That's for a process at constant entropy. We could imagine considering coupling the system to a reservoir, but that just makes things worse. If we couple the system to the reservoir, then we can't cool it in a quasi-static process without cooling the reservoir as well, right? Okay, so thermodynamics is a very depressing subject. The truth hurts. What I want to talk about today is Gibbs free energy. And this is a sort of natural generalization of what we've already discussed. I'm going to introduce another type of contact. We've talked about diffusive contact and thermal contact. we haven't yet talked about mechanical contact. And by that I mean that there's some volume shared by the system and a reservoir, or potentially by two systems, but let's consider a system and a reservoir. Here there's some movable boundary between system and reservoir. It can go up or down. Well, when it goes up or down, the system volume can change. It can increase or decrease. But the sum of the system and reservoir volume stays fixed. Right? So in the case of thermal contact, there was some conserved energy shared by system and reservoir, so that whatever energy the system gained, the reservoir lost, and vice versa. Similar for diffusive contact, there's some conserved number of particles shared by system and reservoir, so if the system gains particles, the reservoir loses them. So here we're saying the same thing about volume. So if the reservoir has some fixed pressure, well, when the system and reservoir come to mechanical equilibrium, the pressure of the reservoir in general will be equal to the pressure of the system, so that the force acting on the movable boundary between the two exerted by the system is balanced by the force exerted by the reservoir. That's the condition for mechanical equilibrium. So if we, in general, have a system in contact with the reservoir, and the contact is both thermal and mechanical, as usual, we imagine the reservoir is huge compared to the system. So when its energy changes a little bit, or its volume changes a little bit, its temperature and pressure don't change. So the reservoir has some temperature tau and pressure P, which are constant. Don't change when the system gains or loses either energy or volume. So in mechanical equilibrium, the pressure of the system will match that of the reservoir. And in thermal equilibrium, it'll have temperature matching the temperature of the reservoir, as we've already discussed. Okay? So this is the type of situation that's often of interest in chemistry. We have some system, maybe where a chemical reaction is going on, but the system is open to the atmosphere, so it maintains both pressure and temperature equilibrium with its surroundings as the chemical reaction proceeds. Actually, let's just back up and remember for a moment, since I guess we haven't talked about it for a few lectures. The corresponding statement for the case of thermal contact which led us to the notion of Helmholtz free energy. So if we have a system in thermal contact with a reservoir which has a fixed temperature, then the Helmholtz free energy is a useful quantity because it tells us when the Helmholtz free energy changes, how much useful work the system can do. There will be some change in the internal energy of the system which results just from maintaining the thermal equilibrium between the system and the reservoir. When we change some other parameter, there will be some heat flow from system to reservoir, reservoir to system, to keep the temperature the same. And that's something that we can't control or use. So we're really only interested in the change of the free energy, the net change in energy, not including the change that needs to take place in order to maintain thermal equilibrium. Okay? So, in general, when we speak of work done by system, it's the change in the internal energy, done on system, minus the heat flow. So in other words, if we do work on the system without any heat flow, then its internal energy goes up. And if we're not doing any work on the system and positive heat flows into the system, then its internal energy goes up. Right? Now, when we're in contact with a reservoir with some fixed temperature, then dq, or minus dq, is just minus tau d sigma. And so, if we consider an isothermal process, the work done can just be written as, well, it's du minus tau d sigma, where tau is fixed, but I can describe that as the change in u minus tau sigma, or the change in the Helmholtz free energy. So we keep track of the change in the internal energy, which is available to do work anymore later on, but we don't include the change in the internal energy that results from the unavoidable heat flow between system and reservoir to maintain temperature equilibrium. So the change in F we can think of as work done on system isothermally. We do work on the system at constant temperature, it increases its free energy, and we can withdraw that free energy later on to do useful work. So now if you want to consider mechanical equilibrium as well, there's some work, which I'll call the mechanical work, resulting from its change in volume, minus pdv. Okay, so dv is, v is the volume of the system. So when the volume goes down, we compress the system, then the work done on the system, the mechanical work, is positive. In mechanical equilibrium, the total work done is the sum of this mechanical work plus the rest, which I'll call the available work. So this is work that has to be done just to maintain pressure equilibrium with the reservoir. So the available work is just, if we're considering a process which is both isothermal and constant pressure, the work is the change in the Helmholtz free energy, since it's an isothermal process. Yeah?
I have a question. So is dW like a differential, or is it dW with like a bar through it?
It really has a bar through it. And the reason I didn't draw the bar is because since I'm talking now, why did we put the bar in last time? It was because we wanted to consider a closed cycle which had both isothermal and isentropic strokes, right? And so the net work done in a closed cycle could be non-zero. But if I just stuck with an isothermal process where I kept the temperature fixed and I reversed it, then the work done, say during compression, would exactly be compensated by the work done by expansion. So the distinction isn't so important here. So in other words, the change in free energy has two parts. Part is the mechanical work that we've got to do to maintain pressure equilibrium, and the rest is a change which we might be able to exploit later on to extract work from the system. That's what I'm calling dW available. And so I can write dW available as the change in the Helmholtz free energy minus the mechanical work done on the system, and that's dF plus P dV. And if I'm considering a constant pressure process, I can call that the change in F plus PV. And this is the quantity I'm going to call G, which is the Gibbs free energy. Okay? So conceptually it's the same thing as when we went from internal energy to Helmholtz free energy, because we wanted to keep track of work done other than that maintain the temperature equilibrium, and now we're extending that and considering work done other than that used to maintain temperature equilibrium and mechanical equilibrium with the reservoir at a fixed temperature and pressure. Of course, you can also describe this in terms of the combined system and reservoir seeking its most probable configuration. So again, going back to the case previously considered a thermal contact, I'll remind you of that. So when we bring the system into contact with the reservoir, it will seek the configuration with total entropy, the sum of system entropy and reservoir entropy. It'll try to maximize that. That's its most probable configuration. And because of energy conservation, so because the total energy is fixed, if the energy of the system increases by dUs, there's a corresponding equal and opposite change in the energy of the reservoir. So the condition for the total entropy to be stationary to first order in the change in the energy, we could write as 1 over the temperature of the system minus 1 over the temperature of the reservoir times the change in the energy of the system. So the amount of internal energy in the system would adjust with a corresponding change in the temperature of the system until the temperature of the system and the reservoir match, and that's the most probable configuration. So in equilibrium, or in other words, in the most probable configuration, system and reservoir are at the same temperature. And if, again, the reservoir is very large, its temperature is a constant. So the system comes to equilibrium by attaining the temperature fixed temperature of the reservoir. So if we consider the temperature of the reservoir to be a constant, then the temperature of the system is equal to that temperature in equilibrium. Of course, another way to say the same thing, which I guess is the way I said it a minute ago, is that in a process with tau fixed, the free energy is minimized. So in particular, it's stationary to first order. So in equilibrium, systems free energy is minimized. And so in particular, we talked about the concept of a Legendre transform. Let me remind you about that. The internal energy of the system we can think of as a function of the entropy. But under a Legendre transform, we trade that in for a function of the temperature. The Helmholtz free energy, a function of the temperature. And we can think of it this way. The free energy, a function of the temperature, is equal to the quantity U minus tau sigma. And it's evaluated at a particular value of sigma, namely the value such that the first derivative with respect to sigma of this expression is equal to 0. So I'll call that stationary with respect to sigma. WRT means with respect to. How about stationary in sigma? Maybe that's easier. So if we adjust the temperature a little bit, the internal energy of the system changes a little bit so that U minus tau sigma remains stationary with respect to sigma, and its value where it's stationary defines a function of temperature. That's the Helmholtz free energy. So I can ask, how does the free energy change when we change the temperature a little bit? So now, there are going to be two contributions to dF, one coming from the change in the temperature, one coming from the corresponding change in sigma, but sigma adjusts so that this quantity stays stationary with respect to sigma. So the first order change in F, or in U minus tau sigma, is du minus tau and d sigma minus sigma d tau. But that's equal to 0 to first order. So the change just comes from minus sigma d tau when we change the temperature. So there are other parameters that we're keeping fixed, like the volume and the number of particles. Yeah.
Can you be more specific on what you mean by stationary?
Yeah.
What exactly?
Stationary means derivative with respect to sigma of u of sigma minus tau sigma equals 0, which of course just means that du d sigma, which is the temperature of the system, is equal to tau. Okay? So in other words, think of tau as a parameter, which is the temperature of the reservoir, and we change the temperature of the reservoir a little bit. Well, then the system has to adjust its state so that its temperature still matches the temperature of the reservoir. That's the stationary condition. Okay? So there are other parameters that I haven't written down, like the volume and the number of particles, which I'm holding fixed when I consider changing the temperature. So the derivative of free energy with respect to temperature when those other things are held fixed, like volume and number of particles, is just minus the entropy. And that's what we learn from this. Okay. And actually, remember that to first order, there's a thermodynamic identity that tells us how the internal energy, there are various ways of writing it, but it tells us how the internal energy changes when there's heat flow. Well, that doesn't look right. Tau d sigma, mechanical work done, and also flow of particles against some chemical potential difference. So here, by considering changing the temperature, we've obtained a Helmholtz free energy, which is now a function of the temperature. But it's also, like the internal energy was, still a function of the volume and the number of particles. So the Helmholtz free energy is equal, when we consider its first order change, to minus sigma d tau. That's what we just derived. But the first order change, when we change the number of particles and the volume, is still the same as for the internal energy. Okay, so now we want to generalize the situation and consider not just thermal contact with the reservoir, but also mechanical contact with the reservoir. We'll continue to consider the temperature fixed, so the system stays in temperature equilibrium with the reservoir. But we'll also allow mechanical contact. So now, the system and reservoir together are going to want to minimize their Helmholtz free energy. So F total, which is the sum of the free energy of the system, the Helmholtz free energy of the system, plus the free energy of the reservoir, is minimized. We can adjust the volume of the system, but there's a corresponding change in the volume of the reservoir. So as we change the volume of the system and the reservoir and the system have some fixed well, the reservoir has some fixed pressure P. The first order change in the total Helmholtz free energy will be minus the pressure of the system plus the pressure of the reservoir times the change in the volume of the system. And when we're in mechanical equilibrium, that'll be 0. So in other words, the pressure of the system matches the pressure of the reservoir in mechanical equilibrium. That's the configuration that minimizes the Helmholtz free energy.
I have a question. Aren't we supposed to minimize the Gibbs free energy too?
Well, that's what I'm about to derive, right? We're going to minimize the Gibbs free energy. So here what I'm talking about is, suppose you bring the system into contact with the reservoir, and the system and the reservoir have different values of the pressure. Okay? So we're actually not in the most probable configuration. The system can find a more probable configuration by changing its volume, borrowing that volume from the reservoir. And so it will decide what its volume should be by minimizing the total Helmholtz free energy. Okay? And it will satisfy that criterion by attaining a pressure which equals the pressure of the reservoir. Okay? And now, equivalently, I can describe that by saying that in mechanical and thermal contact with the reservoir, the system will minimize its Gibbs free energy. Because if we take the pressure of the reservoir as some constant, which doesn't depend on the volume of the system, then 0 equals d Helmholtz free energy of system plus P d volume of system. Or in other words, the first order change in F plus PV is 0. So in thermal and mechanical contact with the reservoir, dG is equal to 0, where G equals F plus PV. Okay?
But how did you get that 0 over there? How did you start with? Just write 0.
Right, so I'm saying that the first order change in the total free energy is dF system plus dF reservoir. dF reservoir is minus pressure of reservoir times d volume reservoir. D volume reservoir is minus d volume system. So this is just dF reservoir. Okay, but for some fixed pressure of the reservoir. Okay? So the criterion that the system minimizes its Gibbs free energy, G, is equivalent to the criterion that system and reservoir together minimize the Helmholtz free energy, where the reservoir has a fixed value of the pressure P. So again, we can obtain a function whereas the free energy is a function of temperature, volume, and number of particles. We can do a Legendre transform to obtain a function g, which we can regard as a function of the temperature, the pressure, and the number of particles. Namely, by g, tau p and n, I mean f of tau volume and n plus PV, but evaluated where it's stationary in V. In other words, we take this quantity for some specified pressure and temperature, we find the volume such that it's at its minimum, and in particular, therefore, its first order variation vanishes. And that determines a function which depends on temperature and pressure. We haven't done anything with the number of particles on either side, but we traded in the variable volume for the variable pressure by doing this Legendre transform. So we obtain the Gibbs free energy as a function of temperature and pressure. And so, same argument as before, but now applied to the variation of the pressure and the volume. I can say, ask, what happens if I change the pressure a little bit? How does the Gibbs free energy change? So it's equal to dF plus PdV plus VdP. This doesn't contribute to the first order change, because we evaluate G by choosing V so that F plus PV is stationary. Now this is the first order change, or in other words, if I take the partial derivative of Gibbs free energy with respect to the pressure, keeping the temperature and the number of particles fixed, that's equal to the volume. So I can write down another thermodynamic identity describing the first order change in the Gibbs free energy, where now I'm considering the independent variables to be temperature, pressure, and number of particles. Namely, dG is equal to minus sigma d tau plus VdP, and then plus mu dn. Okay, so as I've said, we can think of the Helmholtz free energy as a useful quantity if we want to keep track of the change in energy that's available to do work if we work at a constant temperature. And likewise, the Gibbs free energy is useful for keeping track of how much energy we have available to do work if the temperature and pressure are fixed because of thermal equilibrium with the reservoir at a fixed temperature and pressure. So what does this work? What's an example of the type of work that can be done which isn't mechanical, which doesn't have to do with the system's volume changing? Well, one example that we've already discussed and is sort of implicit in our expression, which involves mu dn, is chemical work. So in other words, if I have two systems and both are maintained at temperature tau and pressure P, but there's a chemical potential mu1 for system 1 and number of particles n1, mu2 n2 for system 2, and I have a gadget that I can use to pump particles between the systems, say from system 1 to system 2. Suppose that I pump a number of particles from 1 to 2, call it delta n, then the amount of chemical work done is the difference between the chemical potentials, mu2 and mu1, times the number of particles moved. Okay? So if mu2 is larger than mu1, I'm pushing particles uphill. I guess this is the work done by the system then. No, it's the work done on the system. Right. We're doing work on the system. We're pushing it uphill. When mu2 is greater than mu1 and particles are flowing from 1 to 2, we're putting the system into a higher energy configuration, and later we can let the particles flow back and convert that energy that we've stored to useful work. Okay? Yeah, that's right. So the Gibbs free energy keeps track of the amount of work if I keep the temperature and pressure fixed. Right.
Okay.
And in fact, I'm going to make that even slightly more explicit now. Well, let's remember the distinction between extensive and intensive quantities. So extensive quantities have a value which scales linearly with the system size. So here's a big system. Actually, let's suppose I consider a small subsystem, a box that contains part of the system, and then I let the box get bigger and bigger. Okay? Then the extensive quantities are, for example, entropy, volume, energy, number of particles. All of them scale linearly with system size, the volume, or the number of particles. So all are proportional to n. Whereas intensive quantities keep the same value as we let the box get bigger and bigger and bigger, such as the temperature or the pressure or the chemical potential. So they're independent of system size or independent of number of particles as we scale the system up. Now I can always get an intensive quantity from an extensive one by dividing by another extensive quantity, like, say, the number of particles. So in other words, I can say that U, the internal energy, which is a function of sigma v and n, I can write that as number of particles n times little u, the internal energy per particle. So if U is extensive, as it is, and so is n, then little u, the energy per particle, is intensive. Because it's intensive, I can write it as a function of quantities that are intensive. This quantity doesn't care how big the system is. So it's a function of sigma v and n, but it's only a function of the size-independent ratios of these quantities. So I can think of it as a function of the entropy per particle, sigma divided by n, and the volume per particle, v divided by n. Okay? And, of course, I can say the same thing about free energy or Gibbs free energy, which I can add to my list. of extensive quantities. Helmholtz free energy depends on temperature, volume, and number of particles. So I can write it as n times Helmholtz free energy per particle, which has to be a function of intensive quantities, the temperature, and the ratio of volume to number of particles. The Gibbs free energy is a function of two intensive quantities, temperature and pressure, and the total number of particles. So if I factor out the total number of particles, little g, the Gibbs free energy per particle, has to depend on intensive quantities that I can obtain from tau, p, and n, but those are just tau and p, right? Because I have no other extensive quantity to divide by n. So the Gibbs free energy per particle is just a function of the temperature and the pressure. Now the chemical potential, according to this version of the thermodynamic identity, is the same thing as the derivative of Gibbs free energy with respect to number of particles if we keep pressure and temperature fixed. So I can write mu as dg dn at constant temperature and pressure. Okay, but if keeping the temperature and the pressure constant, I'm just differentiating the n in front. So the chemical potential is the same thing as little g. The chemical potential is the Gibbs free energy per particle. So we can write the Gibbs free energy as n, the total number of particles, times the chemical potential, where the chemical potential is regarded as a function of temperature and pressure. Maybe I should write explicitly that its arguments are temperature, pressure, and number of particles. So why don't we just talk about the chemical potential? Why do we need this concept of Gibbs free energy? Well, what I just said applies in the case where there's just one species of particle, okay? One type of particle, and the number of particles of that type is capital N. But we'll often be interested in systems where there are different species, particularly in chemistry. If we consider chemical reactions, we have some reactants and some products. So each type of molecule is a different species, and the chemical reaction can actually change the numbers of particles of each type, but subject to some constraints. But if we suppose that there are various particle types and each type is conserved, then each one has its own chemical potential. Okay? So if we have multiple species, we can say there's a number of particles of type 1, N1, number of type 2, N2, and so on. Then the chemical potential for species I can define as the derivative of Gibbs free energy with respect to the number of particles of type I with temperature and pressure fixed. Now, when we say that G is intensive, well, we really mean this if we have many species. If we make a bigger and bigger subsystem of a big system, the number of particles of each type, they all scale together. They all scale with system size, right? So if we scale up the system size, we're considering multiplying N1 N2, and so on. I won't write the temperature and pressure explicitly, but they're also. So we scale up the system size by a factor lambda. That increases N1 by the factor lambda, N2 by the factor lambda, etc. The Gibbs free energy is extensive, therefore it also scales up by the same factor, lambda. It's proportional to the system size or volume. And so I can write that as lambda times the Gibbs free energy when the number of particles of each species are N1, N2, N3, and so on. Okay? That's just another way of saying Gibbs free energy is extensive. Okay? When all the particle types scale up together, the Gibbs free energy scales by the same factor. So I can differentiate both sides of this equation with respect to lambda. Now dd lambda of lambda g, n1, n2, etc., is just g. N1, N2, etc. And that's equal to dd lambda g of lambda n1, lambda n2, etc. So if I differentiate that, I have n1, well, I have a sum over I of ni, partial derivative of Gibbs free energy with respect to ni. And here I'm taking the partial derivative with temperature and pressure fixed, but also the number of all other species fixed, aside from ni. And I should have said that up here. I'm considering varying the number of particles of just type I, keeping the others fixed, to define the chemical potential. Okay? And then if we set lambda equal to 1, I actually still have lambdas in here, but if I set lambda equal to 1, then that's just the sum over species of ni times chemical potential of species I. Okay? So in the case where we do have many species, I can write the Gibbs free energy, a function of temperature, pressure, and one blah blah blah, as a sum over species of number of particles of type I, chemical potential of species I. This is an intensive quantity. It depends on the temperature and the pressure. It can also depend on something else which is independent of system size, but that could be any ratio of number of particles of different types. So I'll write ... It can also depend on the ratio of number of particles of type K divided by type J. I don't know, maybe that was confusing. Suppose there are just two types. So I have G tau P N1, N2. And then the chemical potential is N1 mu1 plus N2 mu2, where mu1, for example, is a function of temperature, pressure, and the ratio N1 over N2. Okay. a function of all the intensive quantities. Okay, so how do we apply this to chemistry? So first of all, we want to consider, in order for the Gibbs free energy to be applicable, some chemical reaction which takes place where the vessel in the laboratory is open to the atmosphere. So it has some fixed temperature and pressure determined by the environment. In other words, system has a fixed temperature and pressure determined by reservoir. It stays in equilibrium with the reservoir. And let's say we want to consider, as an example, the reaction in which hydrogen and chlorine combine to make HCl. And there's also the inverse reaction in which two HCl molecules combine and dissociate into molecular hydrogen and chlorine. So we can write that as an algebraic equation. 1H2 plus 1Cl2 plus a minus 2 HCl equals 0. Now for any chemical reaction, I can write down such an equation, which will have the form I sum over the species that take part in the reaction. There's some number now, which I'll call a nu sub I, and some species label a sub I. So this is a label for species to distinguish, in this case, H2, Cl2, and HCl. And this is a quantity of species which characterizes the reaction. For species I. So in this example, in other words, I can say that nu for molecular hydrogen is 1, as is nu for chlorine. Nu for HCl is minus 2. So now, once we turn on this chemical reaction, it's no longer true that N1, N2, etc. are conserved quantities, because the reaction can change those quantities. They can change, but the way they change is constrained by the chemical reaction. Namely, there's a relationship between the change in N1, N2, etc. The change in Ni is proportional to the quantity nu I. All right, so that the chemical reaction takes one step forward, and that will, I guess, the way I wrote it, it's really the opposite. With what proportional includes a minus sign. Okay, I've taken away one molecule of hydrogen and one molecule of chlorine, and I've added 2 molecules of HCl when the reaction goes forward. So the changes are related, constrained by the chemical reaction. So now, when the chemical reaction proceeds, what's the system going to do? It's going to try to minimize its what? Yeah, it's going to minimize G. We're keeping the temperature and the pressure fixed, but now we're relaxing the condition that all the species types are conserved. So a system, in seeking its most probable configuration, will minimize G, subject to the constraint that the particle numbers can only change in ways that are related as prescribed by the chemical reaction. Okay, but we know that we can write G this way. Okay, so if we just have one molecule of each type consumed or created, these ratios change by a negligible amount, so we consider the chemical potential to be a constant. But the coefficients of the chemical potential change. So when G is minimized, what does it mean? dG is equal to the sum over species, chemical potential of the species, change in number of species I. But the chemical reaction says that dNi is proportional to nu I. So this is what we want to be equal to 0 when the Gibbs free energy is minimized. And so this is proportional to the sum of mu I, nu I. The mu i's are the chemical potentials, the nu i's are the quantities in the chemical reaction. So that's equal to 0 in chemical equilibrium. That tells us what the equilibrium concentrations will be, or at least tells us something about how they're related. So just in order to discuss a concrete example, let's suppose we treat the species like ideal gases. Okay, so we have gaseous H2, Cl2, and HCl in a box. The chemical reaction is occurring. We can imagine we can adjust the temperature and pressure, if you like, and when we do so, the concentrations will change. How does that go? Well, we have to use now our expression for the chemical potential of the gas, which I'll treat as an ideal gas. So this is an opportunity to do something that I could have done before but didn't and should now, and that is to talk about ideal molecular gases. Our earlier discussion of the thermodynamics of the classical ideal gas applied to monatomic gases, but there's a little tweak that we have to make if we want to talk about molecular gases, and we should discuss that now, since these are molecular gases. So, consider a molecular ideal gas. let's go back to what we did a few weeks ago when we considered the Gibbs sum for a single orbital in an ideal gas. So we sum over the occupation of the orbital, which can, I'm treating the molecules as bosonic, so there's an activity raised to the nth power, e to the minus n e over tau. Actually, it doesn't matter whether they're bosonic or fermionic, because I'm going to now make the classical approximation of assuming that the occupancy is typically 0 for most orbitals, has a small probability of 1, and a negligible probability of being 2 or more. So for either bosons or fermions, I can write it as 1 plus lambda e to the minus epsilon over tau. Now in the molecular gas, all right, approximate, so we're in the classical regime. So negligible probability for n 2 or more. For the molecular gas, we have to take into account that the molecules can vibrate. You can think of them as, if it's a diatomic molecule, as balls connected by a spring that can vibrate. And they can also rotate. And there's another thing which is important, which is binding energy, if we're going to analyze a chemical reaction. It may be that the reaction is exothermic, so some energy is released when it goes forward, and that means it's going to be favored for the, at low temperature, it's going to be favored for not a lot of energy to be locked into the molecule. You know, the exothermic direction is going to be favored. So we have to keep track of the internal energy of the molecule as well when it's bound. Or in other words, the Boltzmann factor, e to the minus epsilon over tau, favors less internal energy locked in binding a molecule. So, if we're in the classical regime, I now have to change my story a little bit. I'll say 1 plus lambda e to the minus epsilon over tau. But when the orbital is occupied, I should also sum over its internal and rotational degrees of freedom, and include the binding energy as well. So I'll include that all in one sum, which I'll call the sum over internal degrees of freedom, the Boltzmann factor, e to the minus epsilon internal, divided by tau. So the different vibrational states and rotational states have different energy, and I have to include that in my sum of the Boltzmann factor. So this sum I'll just call Z internal. It's the internal partition function for a single molecule. Okay? So our expression for the Gibbs sum I can write as 1 plus lambda, well, I'm just rewriting what I just had above, Z internal times e to the minus e over tau, where this is the external part. In other words, this is the energy of the orbital, the motional energy of the particle when it's in that orbital. What we considered before.
Are you multiplying by z internal, or are you adding z internal there?
I'm multiplying because z internal is the sum. So I'm using the fact that I can write e to the minus e over tau as e to the minus the energy of the orbital plus the internal energy over tau, which I can then factorize. So e to the minus e orbital over tau, e to the minus e internal over tau. And then when I sum over all the degrees of freedom, I'm summing over orbitals, but for each orbital I'm also summing over the internal degree of freedom. So it just becomes a factor multiplying this Boltzmann factor depending on the orbital energy.
And you don't multiply 1 by it?
Multiply 1 by it?
So there's no parentheses around the y and the plus lambda.
Say that once more.
It's not. You're just multiplying lambda e to the negative epsilon over tau by the sum. You're not multiplying 1 by it too.
He is the first.
Yeah, I see. That's right. Because when the orbital is unoccupied, then there's no internal degree of freedom.
Okay.
Right. And this is the case where it's occupied by one molecule, and then I have to sum over the degrees of freedom of that one molecule. Yeah, I see. Okay. And so what it means is that when we consider the distribution function, we should include that contribution from the internal degrees of freedom the expectation value when we're deep in the classical regime for the number of particles in an orbital with energy E will be, I'll call it lambda effective, e to the minus epsilon over tau divided by 1 plus lambda effective, e to the minus epsilon over tau. And this is what I mean by lambda effective, lambda times z internal. And in the classical regime, this is much smaller than the 1, so this is essentially lambda effective, e to the minus epsilon over tau, where epsilon is the energy of the orbital. So we had exactly the same formula before, but now we have lambda replaced by lambda effective. And then a calculation that we did some time ago is when we sum over all the orbitals, weighted by the Boltzmann factor, we get the number of, we get the volume times the quantum concentration, m tau over 2 pi h bar squared to the 3/2. So now the total number of particles, which is the sum over orbitals, sum over E, f of E, is just lambda effective times the sum over orbitals of e to the minus e over tau, which is quantum concentration times volume. So just to write out again what lambda effective is, that's lambda times quantum concentration times z internal times volume. Lambda, of course, the activity, is just e to the mu over tau. Now the payoff is we'll get a modified expression compared to our earlier result for the chemical potential of an ideal gas. We have lambda e to the mu over tau concentration, number of particles per unit volume, divided by quantum concentration times internal partition function of the molecule. And then if I take logs, mu is equal to tau times natural log of n over quantum concentration times z internal. That's the formula that we had before, except now with this additional internal partition function contribution because it's a molecule rather than a single atom in the orbital. So I want the chemical potential so we can obtain the consequences of this condition for chemical equilibrium in the case of where the reactants and products are ideal gases. Actually, we should keep in mind that the quantum concentration depends on the species as well, because it depends on the mass of the particle. So quantum concentration is proportional to mass of particle to the 3/2. So it depends on which molecule in the reaction. Okay, so since I only have a few minutes, let's just notice the following fact. I can write the chemical potential as temperature times the log of the concentration of the species minus log of some constant. So this depends on the concentration of the species, but this doesn't. C depends on species, which species we're talking about, but not on concentration. So in chemical equilibrium, the sum of chemical potentials times nu I, summed over species, is equal to 0. So for our ideal gas case, that's the temperature times the sum of nu I determined by the reaction in question, log Ni minus log Ci, concentration of species I and some constant that depends on the species. So if we exponentiate that, I can get rid of the tau, so this equal to 0, and then I have the product over species in chemical equilibrium. Concentration of species 2 power nu I is equal to the product over species of constant depending on species Ci raised to the power nu I. And this is some constant which depends on temperature and pressure. But the important thing is that when we consider a chemical reaction at some fixed temperature and pressure in chemical equilibrium, this expression is a constant. And that's called the law of mass action. And to derive it, really what we needed was dependence on the chemical potential, dependence of the chemical potential on concentration, which is logarithmic in the concentration, which is true for the ideal gas case, as we've discussed, but also holds true to good accuracy in other cases, like, for example, the case of a dilute solute in a solution, So it can be applied in a lot of situations of interest in chemistry which don't, strictly speaking, involve ideal gases. Okay, I guess that'll do it for today.